Hi there. Want to do a review of the atomic molecular model here for you today, and I have pulled some stuff from various resources here and put them into this page in the shared OneNote notebook that we have. I have some lines here pointing. I just want to show you there are a few other pages I've put in here of resources that you can refer to over there, and of course they won't point to those once we start scrolling down, but those are some other pages that we'll make reference to here in this review of Chem 131 tab. The first resource I pulled here is from something called Chem LibreText, which is another high-quality, free, open source material for chemistry instruction online. There's also other disciplines at LibreText, and I mistyped it Libre, not Lire, so I'll try to inject a B there. That's the file name, so I'd have to go change the file name. So this is a page from that talking about John Dalton's postulation of the atomic theory. The concept of atoms go back to ancient Greece, as far as we know. And their claims were basically that the idea was if you divide something in half and then keep dividing it in half, eventually, as you keep dividing things into smaller and smaller pieces, you'll hit something you couldn't divide. And that thing was called the atom, and that the atom is kind of close to the word indivisible in ancient Greek, I'm told. That was kind of where the Greeks left it, and they weren't good at doing experiments for the most part, and so that idea kind of got abandoned for thousands of years. And then in the early 1800s, John Dalton put together a new atomic theory based on the old one, and he was trying to explain some particular data that was being observed thanks to the new phenomenon of careful experimentation and measurement that Lavoisier and others had brought into play. So Dalton postulated a few things here, that matter consisted of indivisible particles called atoms. Atoms of the same element are similar but differ from atoms of other elements. Atoms can't be created nor destroyed. Atoms of different elements combined with each other in a fixed simple whole number ratio to form compound atoms. Atoms of the same element can combine in more than one ratio to form two or more compounds. The atom is the smallest unit of matter that can take part in a chemical reaction. So you see number 4 and number 5, they're illustrated in red to the side. Water is 2 atoms of hydrogen and 1 atom of oxygen. Hydrogen peroxide is 2 atoms of hydrogen and 2 atoms of oxygen. So we have a 2-to-1 ratio in the first one of hydrogen to oxygen. We have a 1-to-1 ratio of hydrogen to oxygen in the second one. If you look at the ratio between water and hydrogen peroxide, there's twice as much hydrogen in water as there is in hydrogen peroxide relative to the amount of oxygen. Drawbacks to this, atoms have subatomic components. We worry mostly about protons, neutrons, and electrons. There are particles envisioned that people have postulated that are even smaller, but we haven't seen that those affect chemical reactivity. The proton, neutron, electron model seems to explain things better than anything else. Atoms of the same element can be different. They can be isotopes. They can have different number of neutrons. They give the example of chlorine here. There are cases where coincidentally atoms that are from different elements will actually have similar properties, like calcium and argon they mentioned here both have the most common isotopes have an atomic mass of 40. So the ratio gets a little more complicated at time. It doesn't explain things like allotropes, but it does explain a lot of stuff like the law of constant composition, the law of multiple proportions, the law of conservation of matter. And so again, I think this is kind of a nice one-page summary from LibreText that was better than what we had in our textbook. Now, a lot of what you're going to see in the rest of this talk is the illustrations that I've taken from our textbook, and you can always see on these illustrations what the figure number is, and that first number in that tells you the chapter. So that tells you that's chapter 2 where I pulled these. So here we see an image of copper pennies, which before 1982 actually were made pretty much of copper. And then we have an image of the copper atoms arranged in an array. And then here we see a copper oxide in figure 2.3, which is a powdery black compound. And that's thought of as a array where we have copper plus 2 ions and oxygen minus 2 ions that are arranged together. So the formula of that would be CuO, and it exists in a 1-to-1 ratio. There's also a copper oxide that is called copper 1 oxide. I should have put a 1 in this, where the ratio is 2 coppers for every 1 oxygen there. So there's other forms of copper oxides, 2 different formulas of copper oxides. And then 2.4 here shows the illustration of the idea that all the atoms are conserved in a reaction before and after. So you have the sealed bottle, we have the piece of copper that we can see, we have oxygen in the air in the bottle, which is invisible to us, oxygen existing as a diatomic red molecule there, and then they react and form the copper 2 oxide. And again, the idea is that no atoms are changed into other atoms, no atoms are destroyed, no atoms are created. Putting things on a scale here, it's interesting to note how tiny the nucleus of an atom is. So you see here that an atom in figure 211 atom has a diameter of about 10 to the negative 10th meters, and the nucleus of an atom is about 10 to the negative 15th meters, which means that it's about 100,000 times smaller than the atom itself. And an analogy would be if you took a big football stadium and you put a blueberry at the 50-yard line, the blueberry would represent the nucleus, and the stadium would represent the rest of the atom. So just a sense of scale there. Table from the textbook, Table 2.2, shows the different subatomic particles and their properties. We mostly think about the electron, proton, and neutron in terms of the unit charge and the AMU mass, and we consider the electron mass so small as to write it as 0. Over on the right, you see I've written an equation where we have a proton symbolized with a 1 above and below the P to the left. That represents the one at the top, gives you the mass of the particle in AMUs, and the one that's at the bottom gives you the nuclear charge, or the number of protons. In the case of a proton, that's obviously 1. Electrons have a mass effectively of 0 in this notation. And the charge on the electron, it doesn't have any protons, it's negatively charged, so we put a negative 1 down there. And then if you combine those, when you do nuclear reactions like this, you just sum the masses to get the number at the top. So 1 plus 0 is 1, that gets us that 1 at the top in the product side. And then 1 plus negative 1 at the bottom gives us 0. What has a mass of 1 and a charge of 0? Well, that's a neutron. And so that's how we think of neutrons, as being combined protons and electrons. In figure 216 and 220 here, you see some different ways to represent molecules. One of the things that is tricky about chemistry is that you deal with different representations of the same thing, and you have to be able to fluidly go back and forth between those representations and also the reality. So at the top you've got methane, which is the compound that is the prominent, almost essentially all of natural gas. If you use gas heat or have gas to cook on, that's what the methane is. In the lab, that's what would be running a Bunsen burner. And so we can have a formula representation with subscripts there telling us it's 1 carbon and 4 hydrogens. Then we have an array of carbon and some hydrogens there with some lines that indicate the bonding. Those lines represent electrons. and that's called the Lewis dot structure. Then next to that you have a ball and stick model of methane showing its three-dimensional shape, which is tetrahedral. And then we have a space-filling model of that, which maybe is a little more accurate representation of what it might look like if we could see that small. Down in figure 220 we have the very important molecule benzene. Benzene's Lewis dot structure is shown there. It's a six-membered ring of carbon atoms that have alternating single and double bonds, and then each carbon has a hydrogen on it. We see a ball and stick diagram and a model and a space-filling model, and then an actual picture of benzene. When you get into organic chemistry, you will see that organic chemists usually represent benzene just as a hexagon with a circle in the middle of it is a way to represent benzene. So again, there's lots of different ways to represent this, and you have to be aware and get comfortable with those. Now, the next big development in atomic theory was kind of came when we got better at understanding electricity and light, and realized that the light that we can see is just a small component of an electromagnetic radiation spectrum that you see down here in figure 3.3 that runs all the way from radio to gamma rays, and that what makes the light different there is that the wavelength of the light, if we think about the particle model, the wave model of light, that the wavelength is longer down at the radio end and shorter down at the gamma ray end, and that if frequency, which is how frequently the peaks pass in an amount of time, goes the other way, it increases towards the gamma ray end, and that an energy relates directly with frequency, so energy is higher at the other end. So you notice if you look at visible light here and you see that we go from red to violet there. Remember Roy G. Biv over here. I've written it backwards. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. On the violet end of that, we have ultraviolet, which is light that we know is a little bit dangerous, and folks take precautions for it. They wear sunscreen if they're going to be out in the sun a lot. If you're getting dental curing done, as they see in the picture here, they take care for that light to be filtered and for you not to get that light shine directly in your eyes or something. And then you see the stuff up here beyond it, X-rays and gamma rays, are things that we take precautions with. And then below it, we have infrared, and then microwave and broadcast and wireless radio are less dangerous to us. Microwaves are have a different sort of danger to us. What microwaves do is they make molecules rotate. Microwave ovens are tuned to make molecules rotate, specifically H2O. I'll draw an H2O there. And the way it heats up the food is it makes the water molecules spin, and when those molecules are spinning, they're rubbing against other molecules, and that friction gives rise to heat, essentially cooking whatever you're cooking from every water molecule out. So microwave ovens are dangerous for us in that respect, but not so much inherently because they contain so much energy, but just because the energy level is exactly the right one to make that phenomenon happen. This was important. There were several different things that related to light that led to a better understanding of atoms and molecules. One that I'm going to talk about a little bit here more is the idea of line spectra. So you see in figure 313 here at the top, what is labeled number 1 there is a continuous spectrum in the visible spectrum, going from purple or violet all the way down to red. And up at the top, you see that scale is given in angstroms. And angstrom is 10 angstroms are 1 nanometer, and so 4,000 angstroms is 400 nanometers. And so as we're going from left to right, the wavelength is increasing, the energy would be decreasing, the frequency would be decreasing as well. But the big important thing to consider is if you look at this, and particularly look at the hydrogen spectrum where I have an arrow there, you see that when you excite a compound, we get that continuous spectrum at the top. When we excite a pure element, we get these spectra that just have a few lines in them. Most of the spectra is dark. They're just a few discrete lines. And how could something be going on to create just these specific lines? Folks speculated about this, and the comprehensive solution came from a gentleman named Niels Bohr, who came up with something that came to be called the Bohr model of the hydrogen atom. The Bohr model said that electrons could only occupy certain orbits around the nucleus of the hydrogen atom. Those orbits were given numbers, which were called quantum numbers, 1, 2, 3, 4, 5, 6, etc. And on the left here, you see a nice figure that I've taken from the state of North Carolina's chemistry reference sheet, showing the Bohr model and then actually showing each transition and connecting it to the spectrum and showing you the wavelength in nanometers of that transition. Then over to the right, figure 314 shows you the same information in kind of a different diagram, just again to illustrate that idea that you see stuff represented in different ways, and you have to be able to be flexible about moving from one to the other and aware of that. So what we got over here on the right is what would be called an energy level diagram of this. The lowest energy level is down here at the bottom, right next to the figure 314 thing. That's the n equals 1 level. The n equals 2 level is up here. So this transition from here to here would correspond to this transition right here. In this case, what they've done is they've calculated the energy level value for each value of n, and there's an equation for that. And those energy values are expressed as negative numbers with 0 corresponding to the electron escaping from the hydrogen atom. And what you see is as the quantum number goes up, the levels get closer together, and you see that in the other diagram as well. The figure down here, figure 315, shows an expanded energy level diagram with those transitions. You see both absorption and emission here in that diagram, so that's another representation of that. Some of the formulas over here on the left, that energy level value is calculated that way. There's a couple of ways to calculate the wavelength of the transition, or the energy change from the transition, which you could go back and plug that into the h nu or hc over lambda up here to get the frequency or the transition. But the big idea here, the thing that I always tell students is the reason we talk about the Bohr model is not that we want to be able to predict the wavelength of these transitions so much as the idea that what Bohr had proposed here was a really radical concept. What this is equivalent to saying is it's equivalent to saying that you can drive your car at 20 miles an hour, you could drive your car at 30 miles an hour, but you could never, ever, ever be at a speed between 20 and 30. Even when you went from 20 to 30 or 30 to 20, you wouldn't be at the speed between them. It's a statement that utterly makes no sense in the big world that we live in, which is where classical mechanics works. This is in the very small, very fast world of particles inside an atom, and that world is governed by classical mechanics so much as it's governed by a new type of mechanics that we're going to see. And that new type of mechanics came to be called quantum mechanics. Quantum mechanics is based on the Schrödinger wave equation. I should point out I did list some other important ideas here. Really predating the Bohr model, I believe, was the study of blackbody radiation and what was called the ultraviolet catastrophe, that basically involved heating up an object. If you heat up like a piece of metal in a fire, if you've ever done this, you've seen that the metal gets hot, it glows red, and eventually will glow white. So that what that's saying is it's emitting light, and that the wavelengths of the light being emitted are changing as the temperature goes up. And so when physicists tried to mathematically model this and predict this, it didn't work at all. That's why it was called the ultraviolet catastrophe. It predicted stuff that just obviously wasn't going to work. A fellow by the name of Max Planck figured out how to do that. To do that, he invoked this idea that energy was contained in little packets. Those packets the amounts of those packets were given by a constant, which is symbolized by h here, and multiplied by a frequency. And H came to be known as Planck's constant. The photoelectric effect is basically what's behind solar energy. In a way, you shine a light on a metal, and at a certain frequency and above, you will generate an electrical current depending on the metal. And if you measure the energy of those electrons that are being generated for the electrical current, that energy will go up based on intensity, but only above a certain frequency. Below that frequency, you get nothing at all that happens. And a patent clerk in Switzerland by the name of Albert Einstein figured that one out by applying Planck's idea to it, and he called the particle of light a photon, and said that the energy of the photon had to overcome something called the work function in the metal. Once it had overcome that, you started generating electricity, and as the energy went up beyond that, then you transferred more energy to the electron. The idea here that we're doing, what's happening is folks are treating light, which had previously been thought of as a wave, as a particle. De Broglie said, hey, how about if we treat things we thought of as particles, like electrons, as a wave, and came up with some ideas about that, and that contributed greatly to the Schrodinger wave equation, which is an interpretation of electrons as waves, not as particles. The Heisenberg uncertainty principle is another important thing. It came up with the idea of saying that for certain properties, so like energy and position, generally we talk about, that if you know one precisely, you can't know the other one precisely, that there's a limit to the precision of those two things. So the more you know one specifically, the less well you know the other. So if you're, for example, if you're looking at an electron, the way we would detect the position of an electron would be for it to interact with a photon. The interaction with the photon would transfer energy to the electron, so whatever knowledge we had of the energy would be wrong as we became more certain of the position. And so this is what came, and one of the things we see in the Schrodinger equation in quantum mechanics is that we don't interpret electrons as being at a specific location. We interpret them as being in a region, having a probability of existing in a region. So the big equation here that is got second derivatives in 3 dimensions and all kinds of variables here. This is the time-independent Schrodinger equation. The good news is we don't have to solve this equation. The thing in the middle there that looks like a pitchfork is the Greek letter psi. That is the wave function, and the wave function contains information for the electrons. It contains information about the energy and information about the location. And it turns out when you solve these equations, you basically can create your wave functions by putting parts together of different functions that change in different ways depending on these parts. And these parts are characterized in terms of these 4 quantum numbers, n, l, m sub l, and m sub s. So all we worry about in chemistry typically is the values of n, l, m sub l, and m sub s. And the energy depends on n and l, and the location depends on n, l, and m sub l. So we don't even worry so much about the values of those as we do the energy and the location. Over on the left here we have a picture of graphs of these orbitals, as they're called. The orbitals are specified by n, l, and m sub l. At the top we have an s orbital. S is what we call an orbital when L has a value of 0. M sub L, the only value possible for S is 0. And you see that looks like a sphere, and that blue sphere there. over on the right, if you follow the red arrow over to the right, you see three spheres that have been cut, like they've been taken a quarter of a or an eighth of a cut out of. I guess it's a quarter of the sphere has been removed, so we can see the interior of the sphere. And they're getting bigger as you go across there. These are 1s versus 2s versus 3s orbitals. Below it, we have graphs of the wave function squared on y and the distance from the nucleus on x. And that wave function squared is the probability of finding the electron. And what you see is that for a 1s orbital, there's no probability basically of it being at the nucleus, but the probability goes up, maximizes, then goes back down as we go further out. If you look at the 2s orbital, and you see behind the orbital, you kind of have a depiction in blue and red of the cross section of the sphere as you're moving through that. A 2s orbital has a small hump near the origin, and then a place where it goes to 0, and then a bigger hump, which corresponds to the red sphere. So these orbitals are a little more complex. They're not like solid uniform balls. They've got more complex internal structure from them. And that's really what I want you to know from this, is just to realize that when we look at the left here and we look at these pretty pictures of these orbitals, that those have different structures. So at the p orbitals in the next row, that's where L is equal to 1, we get three three p orbitals that are at the same energy level that have different spatial orientations. So from left to right, we have a blue and red. we usually call these dumbbell shapes. On the x-axis, the blue and the red differences basically are talking about different phases of the wave function, or signs of the wave function. In that's not really important in this course in terms of thinking about how those interact, but you might get into that later on. So a dumbbell centered on the x-axis is a p orbital. A dumbbell centered on the z-axis is a p sub z. Sorry, the first one was p sub x, p sub z, and p sub y orbitals there. Then at L equals 2, we have the d orbitals, and they're depicted there. And then at L equals 3, we have the f orbitals, which are even more complex. Generally the p is a 2-lobe dumbbell. Most of the d's are 4-lobe dumbbells, and most of the f's are 8-lobe dumbbells, with some spectacular exceptions. You have to kind of, I don't know about you, but I like these ones that are a dumbbell with an annulus around it, like the d z squared here, and the double annulus one here, and the d's. Those are just kind of cool graphs. Now, again, in chemistry, we're going to represent things differently, and we're going to represent things oftentimes in an energy level diagram. And again, energy is going up, and you see the 1s orbital is at the bottom, and then we go up to the 2s orbital, and then we go to the 2p orbitals, and there's 3 of them, and then the 3s, there's 1, and then 3p orbitals. And you see that, generally speaking, as the value of n, the number in front of the letter, goes up, the orbital increases in energy. But you see circled here an exception. The 3d is actually higher than the 4s, and that's why we say that energy is a function of n and L, L being the term that specifies what that letter is, what type of sublevel it is. Over here in Table 3.1, you have a summary of the 4 quantum numbers and what their significance are. The way that I like to encourage students to think about electron configurations is just to use the periodic table. As you see down here in Figure 3.17, we've got basically 4 regions on the periodic table. The blue region, we say we're filling the ns orbitals, which those where n is given by the period number. So hydrogen and helium would be the 1s orbitals. Rubidium and strontium would be the 5s orbitals down on row 5. Then we've got the salmon or pinkish color there, where we're filling the np orbitals. So from boron to neon, it's the 2p. From tellurium to radon, down on row 6, that's the 6p orbitals. And then in the middle, we have this yellow region, which is the d orbitals, and the numbering for those d orbitals is actually the row number -1. So on row 4, after we fill the 4 s orbitals, we then are filling the 3 d orbitals from scandium to zinc. And then finally down at the bottom we have the f orbitals, which come off of the periodic table in the boxes circled in red there. Those are numbered as the row number -2. So the row starting with cerium comes from the lanthanum on row 6 there. So cesium and barium are the 6s, lanthanum would be a 5d, and then when you jump down to cerium, we'd be filling the 4f orbitals. And these oftentimes are ones that you would find that they don't always obey the rules in terms of just adding electrons to them, and in terms of whether it goes in the D or the S. It's quite complex. We'll be focusing more on the ones that are in the blue and the salmon, the S and P's, with a little bit of attention to the D's. Over here on the right, I said let's figure out how to do this by imagining each box as 1 electron. So let's look at selenium. I circled selenium here. I'll circle it again. It's right here in the periodic table. What we're going to do is start at the beginning at element number 1 and count through the periodic table. So hydrogen and helium tell us that that's 2 electrons, 1 s2, each box representing an electron there. Lithium and beryllium, 2 more electrons in the 2s orbitals, so 2s2. Boron through neon gives us the 2p6. Sodium and magnesium gives us the 3s2. Going from aluminum to argon, we get the 3p6. Potassium and calcium give us the 4s2. Scandium to zinc give us 3d10, and gallium to selenium, we count 4 boxes over, so it's 4p4. If we want to talk about the ion, if we add 2 electrons to that selenium, then we just moved right 2 more boxes. So instead of gallium to selenium, we'd be going to gallium to krypton, and that would be a 4p6 in that case. And so we say that selenium -2, which would be called selenide, is isoelectronic with krypton, meaning it has the same electron configuration. Conversely, if we wanted to take 2 electrons from selenium, not that that's common in terms of what selenium does, that would go back 2 boxes, so it'd be isoelectronic with germanium here, and then it would have a 4p2 ending to its electronic configuration. We also talked in this chapter, in chapter 3, and also down, I think, in chapter 5. Make sure, I think I pulled a few things together there, about things that are called periodic trends, things where you can look at the periodic table and you can have an idea of the relative properties of different elements. So the first periodic trend we talk about is atomic radius. Generally speaking, atomic radius goes up as you move down the periodic table. That makes sense. Lithium has more electrons than hydrogen. Sodium has more electrons than lithium. Potassium has more electrons than sodium. They're going to be further out there and further out energy levels. Perfect sense. What doesn't make sense initially is the idea that as you go across the periodic table from left to right, the atomic radius actually goes down. So the biggest atom here, as you see in the pictorial representation of this, is francium. Usually we say cesium because francium is, all francium atoms are radioactive. So if we talk about building, say, a photocell, we want to have an element that's the easiest one to get electrons off. That's going to be cesium. And again, that's what the definition of, jumping ahead, getting ahead of ionization energy. We'll talk about that in a minute. The way we explain this is through this idea of lower effective nuclear charge. The effective nuclear charge is called Z star or Z effective, where Z is normally the atomic number. So I have a little model over here. I've got lithium, and this is a very simple model of this. If we imagine the lithium having 3 protons here in its nucleus, and then having 3 electrons out here one of which is out in the 2s, and the other two are inside of that in the 1s2. If we think about the electrostatic force felt by this electron that's out here in the outermost orbital, looking back at the nucleus, it's going to be attracted to the nucleus where there's three positive charges, but these two electrons in between it kind of mask that, and they wouldn't mask it 100%, but if we just assume for simplicity's sake that they masked it 100%, that would give us an effective nuclear charge of 1. If we look at the next element on the periodic table, at beryllium, beryllium's got 4 protons, and 2 of the electrons are in the 1s orbital, 2 electrons are in the 2s orbital. Now when one of the outermost electrons is looking back at the nucleus, it sees the 4 protons in the nucleus, but they're only masked by the 2 electrons in the 1s orbital. Again, we're assuming in this simple model that the inner electrons mask 100% effectively, and the electrons in the same level don't mask at all. That's not bad, it's not exactly true, but that we still see here that the effective nuclear charge goes up, which means that it's going to be more strongly attracted to the nucleus and it's going to come in. The periodic trends here, these figures above or below them, you have a depiction of the trend in terms of actual representation of the data in the periodic table, and then you have a graph of the trend as well. So this is atomic radius over here on the left. Over on the right we have something called ionization energy. Ionization energy is the energy if we take an atom and we remove an electron from that atom and make it a positive 1 charge, that energy is called the first ionization energy. If we removed another electron, it'd be the second ionization energy, etc. And you see that the values in the periodic table here, if you look, the lowest value is down here at cesium. The highest value is up here at helium, and that goes along with the atomic radius trend. It's a simple idea that if the outermost electron is further away, that is, it has the biggest radius, it's going to be the easiest one to pull off. So one of the things you see is that you have and you look at the subsequent ionization energies here, these ones that are shaded in green are the ones that are noble gas configuration, and you see my red line there. If you cross that red line going across in each row, you see the value jumps up tremendously, and that's because that we're isoelectronic with a noble gas configuration in the green highlighted items. Sometimes I've seen questions where students have been asked to tell what group an element's in based on ionization energy numbers. Over here on the left, we've got the electron affinity as another periodic trend. This is sort of the opposite of ionization energy. We're adding electrons to atoms to make them negative. So this kind of talks about how much electrons won't pick up, or atoms won't pick up electrons. And the value here, if it's negative, it's favorable. So the element that most wants electrons is fluorine. And these atoms over here do not want electrons. The noble gases, they aren't going to pick up electrons at all. Looking at the rest of them, you see over here on the left-hand side of the periodic, generally it decreases going that way. That's the electron affinity trend and some actual data there for it. Now, jumping over to chapter 4, another trend that was discussed there, which I thought we'd just talk about here, is a very important trend called electronegativity. We'll talk more about it below. The values increase as you go to the right and up on the periodic table, where fluorine is the highest value. Hydrogen's value would always place it right between boron and carbon, which is important to recognize. So this is probably the most important periodic trend to know in subsequent chemistry classes. From the periodic table, we have names of the groups that you see over here in figure 336. You should be aware of those. And then we have some common ions that exist, and frequently you see that these are isoelectronic with the noble gases. The ones in the middle here are a little less well known, a little harder to predict, a little harder to explain. But the ones that are in groups 1, 2, and 13 through 18, which are called the representative elements, or the main group elements, every one of those is isoelectronic with a noble gas. Then moving on in Chapter 4, we talk about ionic compounds. We depict them as these extended arrays of positive and negative ions. So you have sodium chloride in the figure 4.3. You also remember that you basically do the cross the charge trick to figure out the formula. So if I had sodium and oxide, it would be Na2O. We typically call these formula units instead of molecules because you can't say which cation goes with which anion. Cations being positive charged ions and anions being negatively charged. Looking at moving on to covalent bonding, where we share electrons to become sort of isoelectronic with the noble gases, and we call that typically the octet rule. First of all, there's kind of an energetic picture that I like to keep in mind. This is a graph that's the energy of interaction on the y-axis with the distance between atoms on the x-axis. This is actually for hydrogen here, but you could see graphs like this for any pair of atoms you want to predict. At a large distance, they don't interact. The energy is zero. As they come together, the interaction energy is negative or favorable, and then it reaches a point at which it turns up and becomes less favorable. So the bottom of that well there that distance corresponds with the bond length, and then the distance from the bottom of the well to the zero line, that's our bond energy, or bond dissociation enthalpy, or it has several different names that folks use, but that's a reminder that forming bonds gives off energy. Now, we talked before about representing elements differently, and again, this is a point where I would point you to that visual method of valence bonding handout that you might want to look at. We think about looking at what we call the valence electrons, which are the outermost electron, the highest energy level electrons, and we represent those valence electrons in what we call Lewis dot structures. So if we're looking at, let's say, sulfur here, I've drawn kind of a rough periodic table with these dot structures. Sulfur, of course, is 1s2, 2s2, 2p6, 3s2, 3p4. These are the outermost valence electrons in sulfur. That's 6 electrons, 2 here and 4 there, and you see the 6 dots in sulfur that way. Again, we're dealing with the representative elements, or the main group elements, groups 1, 2, 13 through 18. And going across as we write these dots, if the dots are written together, they're less reactive. And if the dots are written separately, they're more reactive. And one of the things you see that's different from how pairing of electrons work in a electron configuration or an orbital diagram is that we don't pair electrons until we have 4 unpaired electrons, and then we start pairing them over here in group 15 with nitrogen. So those are the atomic Lewis dot structures there. We can then put those together. So if we were talking about water here, I've got a H and another H and an O, and I've got their Lewis dot structures here, and we can see we have unpaired electrons that can easily pair up and form this structure here to the right, where I've written a single line for the water. And for H, line O, dots above and below it, pairs of dots above and below it, and line to another H. The dots above and below are called lone pairs. The lines represent bonding pairs. A single bond has 2 electrons. And my circles here are to count the electrons for each atom. And the rule in covalent bonding is that any electrons in a bond get counted for both atoms that are in the bond. So this pair of electrons right here gets counted both for hydrogen and for oxygen. So this hydrogen has 2. That's exactly like helium. It's a noble gas configuration. So that obeys the octet rule, or really we would call it the duet rule for helium, but we usually just call it the octet rule because most things are 8. Oxygen has 2 bonds, 4 electrons each, 2 electrons each, total of 4, and 2 lone pairs, 2 electrons each, total of 4. 4 plus 4 is 8, so it meets its octet. And then this hydrogen over here has the bond, so it has 2 electrons meeting its duet, so it's good. If you look at the visual method of valence bonding page, this is a step-by-step procedure to make harder structures, and I've depicted here going through doing the structure of carbon disulfide. I calculate initially the number of valence electrons. Carbon is in group 4. There's only 1 carbon. Oxygen is in group 6, and there's 2 oxygens. So that gives me 16 valence electrons, which are represented over here in this valence bin, the valence electron bin. I made a structure, valence electrons needed, valence electrons available chart here. The idea is that I'm going to create a structure and evaluate it based on the valence electrons that it needs to meet the octet rule and the valence electrons that are still available based on what's in the bin. So the first structure, we decided carbon was the central atom because carbon has the lowest electronegativity, and it's symmetrical if carbon's in the center. So both of those conditions suggest carbon might be the central atom. We connect the 2 sulfurs up with a single bond that took 2 electrons, so I marked out 2 electrons over here, which I'll mark out again in black. That left me, from my 16 I started with, that left me with 12 electrons. Then if I do the sort of counting that I did over there with the circles before, the sulfur has 2 electrons. It wants to get to 8, so it needs 6. So H and N here stand for have and need, not hydrogen and nitrogen. The carbon gets to count both of these bonds, so that's 4 electrons, so it only needs 4, and the sulfur over here only counts 1 bond. It has 2, it needs 6, so if I add 6 and 4 and 6, I get 16. 16 is greater than 12. That tells me I have to write a double bond, so I draw a new structure. I remember that I paid for the single bonds already, but I'd mark out 1 more bond up here, 1 more pair of electrons. That lowers my count to 10. When I do my have and need analysis here, this sulfur on the left didn't change, but the carbon changed. It has 6 now, double bond and a single bond, so it only needs 2. And the sulfur on the right has a double bond, so it only needs 4. That adds up to 12. 12 is still greater than 10. That tells me I go and put another bond in. I put the double bond in between the other sulfur and the carbon. And when I do the counts there, that leaves me, I have 8 left, and I wind up needing 8. That's equal. That tells me I can put the electrons in as lone pairs, which I did. I checked 3 things. I checked the formula. I was asked to do CS2. I've got 1 C, I've got 2 S's. That's good. I checked total valence electrons. I said I had 16 valence electrons. If I go through here and count 2, 4, 6, 8 on the double bond, 10, 12 on the other double bond, 14, 16 on the lone pairs on the right sulfur. That's 16. That checks off. And then I check the octet rule around each atom. And remember, the bonds get counted for both atoms. So sulfur has 2 lone pairs and a double bond. That's 8. Carbon has 2 double bonds. That's 8. And the other sulfur has 2 lone pairs and a double bond. That's 8. So the octet rule is met. You could draw a structure like this, which also passes those rules, and the way you tell the difference between those two is through something called formal charge. That's described over in that valence bonding page. If you want to look at that there, you can, but I'm not going to go over it here. Then we take these shapes and we use them to predict the 3-dimensional shape of of the electrons and the atoms. The three-dimensional shape of the electrons we call the electronic geometry. The three-dimensional shapes of the atoms we call the molecular geometry. If there's no lone pairs, they'll be the same. No lone pairs on the central atom, they'll be the same. But they might be different. And what will happen, if you look at the sheet here, I'll pull it up for just a second, that once you pick an electronic geometry, like let's say we have 4, the electronic geometry for those guys are all tetrahedral. Depending on the number of lone pairs on the central atom, you can have 3 different molecular geometries, but you can't have any other molecular geometries, right? So if you decide it's got a tetrahedral electronic geometry, it's not going to be trigonal planar, for example. Keep that in mind. So this lets us predict three-dimensional shapes, lets us predict bond angles. It also lets us predict something called hybridization, which we'll talk a little bit more about. So 2 examples here quickly. Our carbon disulfide, we've got 2 groups with no lone pairs. That tells us that we have a linear electronic geometry and a linear molecular geometry and a 180-degree bond angle. If we look at the water molecule we did before, we've got 4 groups around the oxygen. 2 of those groups are lone pairs. So 4 groups tell us that it's a tetrahedral shape, and the perfect tetrahedral angle would be 109.5, and again that's the electronic geometry. But having 2 lone pairs means that the actual atoms are at a bent or angular shape, and so we usually represent water kind of like this, and we say this angle here is, it actually turns out to be about 104 degrees because those lone pairs take more room than that. The principle here is basically that that electrons don't like each other, that they have the same charge, they repulse each other. It's called valence shell electron pair repulsion theory. I usually expand that to group because a multiple bond is a group of electrons, and those groups of electrons want to get as far apart from each other as possible, and those shapes are the ones that get them the furthest distance apart. There's another page over there for you called Determining Polarity, which gives you a flow chart to determine polarity. This is where we apply electronegativity and shape together to determine some properties of matter. So first of all, let's start over here and look at the electronegativity difference. And generally speaking, what we say is that electronegativity is the tendency for an atom to want electrons that are shared in a bond. And if the difference between the 2 atoms is 0, they share the electrons perfectly equally. We call that a pure covalent bond. If the difference is a little higher, then they don't share them equally, but they're still sharing them. That's called a polar covalent bond. And then past a certain point, they are sharing them so unequally that we can say one electron's been transferred from one atom to the other, and we say that's an ionic bond. I usually say that 0.3 to 1.7 is the polar covalent range. The book here suggests 0.4 to 1.8. Kind of depends on which set of electronegativity values you use. So we have our electronegativity table copied right under this. This is just the same table I had up there before. If we look at a couple of examples here, if I have a lithium and a fluorine, okay, so that one right there, that electronegativity difference, the fluorine is a 4, the lithium is a 1, that difference is 3, that's greater than 1.8, that's an ionic bond. So we would say lithium plus fluorine negative. If we look at carbon and hydrogen, carbon is 2.5. Remember, hydrogen would sit right next to carbon there. It's 2.1 here. 2.5 minus 2.1 is 0.4. And carbon hydrogen is basically what I would suggest is the cutoff there for that. So that carbon hydrogen bond, if we were depicting it, we would depict those 2 electrons being pretty equally shared between the carbon and the hydrogen. If we look at carbon and oxygen here, that difference is 3.5 for the oxygen minus 2.5 For the carbon, that's a difference of 1.0. That's in the polar covalent range. So we would say that those electrons were closer to the oxygen, maybe. Well, of course, we don't usually. We'll just represent it with a line like that, and we might use a delta positive and a delta negative on that. And it doesn't matter whether it's a double or single bond. That stands for a partial positive and a partial negative charge because the electrons are partially shared, or partially more located on the oxygen. And again, we're not thinking so much of electrons as particles here, as we're kind of thinking of the likelihood of the electrons being somewhere. So sometimes we talk about the electron density being higher around the oxygen and lower around the carbon, and representing it that way. Now, back over here on at this point, looking at these figures, we've got some molecules here. And another way of representing this carbon-oxygen, you see here I get my delta positive, delta negative things there, is you can represent them as dipole vectors. And that's the picture right there, where the plus sign is on the positive end and the arrow points to the negative end. And if we look at the shape, carbon dioxide here has a linear shape. It has two dipole vectors that are equal and exactly opposed to each other. Those would add up to be 0. And so we have carbon dioxide as a non-polar molecule. If we look at water over here, water has the two dipoles. Oxygen is partially negative, the hydrogens are partially positive. Because of the lone pairs on oxygen, this molecule is bent. And so now our two dipoles that represent the bonds, this one, this dipole here and this dipole here represent the bond. They give us this resultant dipole that isn't 0. So water is a polar molecule. And so this is a disturbed symmetry due to lone pairs. And then down here we have an example of a compound that's carbon, sulfur, and oxygen. So I don't know what you call that exactly, but it's one sulfur and one oxygen and a carbon. It's very much like CO2 or CS2 that we did before. We just now we have an oxygen on one side, sulfur on the other. Again, it's a linear molecule. It's got polar bonds, but now even though they're exactly 180 degrees opposite each other, they're not equal. So this is an example of different atoms having disturbed symmetry. And if I point to the determining polarity thing, this is just a flow chart. So you take your Lewis dot structure and your 3D geometry, and then you ask yourself, does the molecule contain polar bonds? And here I use a D instead of a delta because the software created this and would let me use Greek letters. If the electronegativity is not greater than that of carbon-hydrogen, then the molecule is nonpolar. You don't have to think about anything else. So over here are some examples of nonpolar molecules. If the answer to this question, in a flowchart, a diamond always gives you a question. If that answer is yes, we have to ask another question. Is the symmetry disturbed enough so that the charge distribution is asymmetric? If the answer is yes, we have a polar molecule. So water, dichloromethane are two examples. If the answer is no, carbon dioxide, carbon tetrachloride, two examples that have polar bonds but don't have a disturbed symmetry or are too symmetric to do that. And that disturbed symmetry, again, I say often shows up as lone pairs on the central atom, like in water, or as different atoms around the central atom, as we saw in the COS example on the other page. There are some exceptions that I point out, but those are good general rules for determining polarity. These are basic skills for organic chemistry, so I do find these to be really important. Moving on, talking a little bit more about advanced bonding theory in Chapter 5. We talk about valence bonding theory, where we basically take our Lewis dot structures and think about the atomic orbitals and try to explain how those orbitals overlap. So in figure 5.4a there you see two 1s orbitals overlapping, and they give kind of a circular, if you think about the cross-section through that along the axis of the bond, it's a circular cross-section. In B, you have an s orbital on the left, and then you have the p orbital, which is the blue and the red dumbbells there. The blue part of that is interacting with the s orbital, and that's again a circular cross section. And then we have in C there two p orbitals coming together end to end and giving that circular overlap again through the red regions of the orbital. And all of those, that circular cross section, because that sort of looks like an s orbital, we call that a sigma bond. And the Greek lowercase sigma is the letter we use there, which looks like an O with a line on top of it. If you have two p orbitals combining side to side, as we see in figure 5, that creates an orbital where the cross section has two circles, essentially a circle above, a circle below. Looks sort of like a p orbital, so we call that a pi bond and use the Greek letter pi as a symbol. In terms of recognizing these in structures, it's really quite easy. The first bond that you have in any case is going to be a sigma bond. If you have a double or a triple bond, the subsequent bonds will be pi bonds. So in HCl here we only have a sigma bond. In O2 we have a sigma bond and a pi bond. In N2 we have a sigma bond and two pi bonds. So counting them out is not so hard. Now, hybrid orbitals are a great example of how you fix a theory. Quantum mechanics, really has some impressive results. Folks do have, continue to search for an even better theory. But one problem with quantum mechanics is that the predictions based on the atomic orbitals as to the shapes that molecules would take didn't always agree with what we knew experimentally about the shapes of those orbitals. And so the way that was fixed was this idea of orbitals combining or hybridizing to give this new type of orbital blend that would explain the shapes. So here we see on the left an s orbital and a p orbital. These are on the same atom. We're just depicting them separately to make it clear what's going on. That if you mix those two together, and I put two orbitals in the hybrid, I get the same number of orbitals out, and I get two sp orbitals, which look like a dumbbell that's more weighted towards one end than the other. Okay, so kind of like a balloon looking thing there. And there's two of them, one pointing in one direction, one pointing in the other direction, one pointing in positive x-axis, the other pointing on the negative x-axis. And then down at the bottom you have the description, or the graph of both of them on the same atom, which is a little confusing. You have to remember those are two separate orbitals even though they're the same color. If we look at the energy diagram down below in figure 5.9, we write the s and the p orbitals, with the s orbital lower and the p orbitals higher. And then when we blend those, the s and the p orbitals combine and make an sp hybrid that's a little above but a little below the energy of the p orbitals, that the s and p orbitals that mix together. And then the leftover two p orbitals are there. And now you see that the two electrons that were in the s orbital actually now are split up and are one each in each of the sp orbitals. One way handy way of remembering this, if you're thinking about your number of groups that you have, which in this graph they call regions of electron density. So again, a group could be a lone pair, a single bond, a double bond, or a triple bond. The number of groups you have around that central atom is going to give you the number of orbitals that are in the hybrid and the number of those orbitals that exist. So two groups give you two sp hybrid orbitals. Three groups gives you three hybrid orbitals that are called sp2s. Four groups give you four orbitals that are sp3 hybrids. And five groups gives you five orbitals that are sp3d hybrids. And six groups give you six orbitals that are sp3d2, or sometimes called, you'll sometimes hear these say p cubed d squared orbitals. And one of the things you gotta remember, if I say 1s2, that 2 means two electrons in the 1s orbital. If I say sp3, that's a description of the number of orbitals in the hybrid. So confusing but similar notations here, and you've got to be able to tease those out. So if we then try to explain the bonding in a molecule, so this molecule that's depicted here is called acetylene or ethine. It's got 2 carbons and 2 hydrogens, triple bond between the carbons, single bonds between each carbon and 1 hydrogen. The carbon-hydrogen bonds are sigma bonds. The first bond in the carbon bond is a sigma bond, and there's 2 pi bonds. The sigma bonds are formed by sp hybrid orbitals on the carbon. As you see here, this sigma bond represented there. If I have an sp hybrid, I've got 2 leftover p orbitals. I've got one that's going up and down, and one's going out and back there. Maybe we would call those, if the axis of the bond is the x-axis, then that's the pz and the py orbitals. And what happens is that those orbitals interact, those p orbitals interact and create pi bonds. So we see the pi bonds there, and again the pi bond is represented, if we have a sigma bond coming from the sp2 sigma bond, the pi bonds, one pi bond has a region above and below, so that's one pi bond, and then we've got another one rotated 90 degrees to it that you can see better in the diagram over there. We're going to leave off molecular orbital theory, and we'll cover that. We'll pick that up in our first unit after the review unit. So hopefully that helped you review atomic structure.